Oh, thank you. I'm delighted to be here. I'm hoping that we're going to have a good time in the next hour. This is a very non-technical presentation. I only have one slide with formulas on it, but I hope to give you some ideas to think about. It's an overview of statistical process monitoring, but also just quality in general. First, I want to point out, as you may know already, Germany has a very good reputation for high quality products. And this particular survey, Germany turned out to be #1. For the sake of my presentation, I wish the United States had been a little higher, but it is what it is here. Now, in order to understand and get an overview of what's happening in industry, I think it's helpful to look at the industry 1.0 to industry 4.0. Primarily based on the technology that has been used. Industry 1.0 is the Industrial Revolution, water and steam power, mechanization from the Industrial Revolution. Industry 2.0, use of electricity and mass production, assembly lines. Industry 3.0 involved more automation, information technology. And now Industry 4.0, we have cyber physical systems, a lot more data. There's a lot involved in Industry 4.0, and I'll talk about Industry 4.0 toward the end of my presentation. One thing to keep in mind is the situation with data. In Industry 2.0, data was scarce. Measurements had to be made manually. So measurements were costly. They didn't have much data. Data storage involved writing numbers on a sheet of paper and so forth. Now, Industry 4.0, data are collected automatically, data are cheap, data are plentiful, and we have cloud-based storage. So we're talking about orders of magnitude difference in the amount of data, and it also has affected the statistical methods that are being used. In Industry 2.0, the focus was on very simple statistical methods. This individual, Wolfgang Wasser, is given credit for coining the term Industry 4.0. In a report to the German government, he included that, and he's given credit for that. Also, coincidentally, he's a graduate of the University of Hamburg, so I thought you might find this interesting. Now, Walter Schuhart is certainly an important figure in the quality area and in statistical process monitoring. The father of statistical quality control. He worked for Western Electric. Western Electric made telephones. So quality was a big issue there. They had thousands of inspectors, something that is discouraged now, the quality by inspection. And one of his main contributions was stressing the time order of data. Now that seems obvious to us now that there's information in the time order of data, but 100 years ago, this was a new idea. So he stressed the time order of data. Also, he came up with a process improvement strategy, plan, do, shape, act, cycle for continuous process improvement that is related to Six Sigma process. You may have heard about Six Sigma. It's a structured process improvement strategy, define, measure, analyze, improve, control, where many companies are using this, and the statistical methods are embedded into the process improvement strategy. I'm not going to talk about Six Sigma any more than this. If you're interested, I can provide more information on this topic. Now, this is an earlier photograph of Walter Schuhart and the first Schuhart control chart. So again, we're looking at time order of data. These are proportions of defective items plotted over time, aggregated by month. So it's important to realize there's a lot of aggregation here. Now we're taking data so quickly, these data were aggregated by month. Now, Schuhart put limits on this figure to capture the sampling variation because he didn't want people reacting to what he called common cause variation. He only wanted people to react to variation that seemed unusual. So a better picture of a Schuhart control chart is given here. We're plotting data over time. We have control limits, upper control limit, lower control limit. There's some natural variation in the process that again, we don't want to react to. But if we have a point that falls outside, like this red point, then we do want to take some action. So it's important to keep in mind, these are statistically based limits. And it's related to sequential hypothesis testing. That's going to come up as an important point later. Now, Schuhart wrote 2 books. The 2 books here on the left, very difficult reading. I'm not sure many people have ever read Economic Control of Quality of Manufacturing Product all the way from the first to the last page. Very hard to read books. The one in the middle, one of my colleagues and I read that one semester, going through it section by section by section. The main thing we learned was time order of data makes a big difference. He's really stressed that point over and over and over again. Now, the Western Electric Quality Control Handbook came out in 1956. It has a lot of good practical advice about what data to collect, how to summarize the data, how to interpret the data. And I found that now a lot of the books on statistical quality control focus on the mathematics, and they kind of don't spend enough time talking about the practical aspects of data collection and so forth. This book still has a lot of valuable information in it. Now, Schwinn found this paper written by a German author. It's interesting to know this was written before Schuhart's first control chart, where he's making the same point that the time order of data contains valuable information. And here he demonstrates a cyclical pattern, which is common in industrial data. And also on the right-hand side here, the process has kind of gone haywire. But he was making the same point as Schuhart, but he didn't put the limits in there. I think the limits are useful because humans have a tendency to overinterpret patterns. And if you don't have limits, there's a tendency for operators to over-adjust a process and increase the variation. Now, if your job is to do process monitoring, the first step is to collect some baseline data. There's a lot to be learned from baseline data. There may be clues for process improvement. We look for outliers. We look for other sources of instability. Are the data autocorrelated? Do we need to put in extra variance components? There are a lot of decisions and a lot of learning in phase 1. And I don't really think that phase 1 gets its due in the literature, because phase 2, the ongoing monitoring, fits better into a mathematical framework. Phase 1 doesn't really fit into a mathematical framework very well because it's really messy. But in our paper that we wrote a few years ago, the first half of this is devoted to phase 1 issues, practical issues related to phase 1. All right, so we have phase 1, understanding the process, getting a baseline. We can fit a model, estimate the parameters of the model, and move on to phase 2. Now, phase 2, we're collecting data sequentially. We're looking for changes from the baseline model, and it's important to monitor both the mean and the variance. If the mean of the process characteristic changes, we want to know about it. If the variation changes, we want to know about it. So again, we have 3 sigma limits. The upper chart here, we're plotting sample averages. The bottom chart, we're plotting sample ranges. We want to detect changes in the mean or changes in the variance. Again, this could be looked at as sequential hypothesis testing. A very common approach still in industry now. Now, why do we want to detect changes in the mean and variance? Well, it's because quality characteristics have an ideal target value. Say you're making a part for Mercedes. They're going to tell you what the length should be. That is the target value, but they're going to give you a little bit of wiggle room in there, where if you're within this interval, the part is conforming. If it's outside this interval, it's said to be non-conforming. Now, this terminology has changed over the years. It used to be that if you were outside the limits, the part was defective, but that was too strong. No company wanted a lawsuit where they had to admit they produced 1% defective products. These parts are not necessarily defective, they're just not as good as what we want them to be. So I think, if somebody calls you non-conforming, that could even be a positive thing, right? Somebody calls you defective, it's kind of hard to put a positive spin on that. So it was a change in terminology. So if the variation is really tight around the target value, then we have what is called a capable process. Now this is an example. Collect some data from a process, it's stable. We form a histogram here. The specification limits are in red. These specification limits are determined based on engineering considerations. Control limits are based on statistical considerations. So there's a fundamental difference there. But this is not a capable process. There's too much variation. If the target is 100, we're pretty close to that, but there's too much variation. We don't want parts outside the specification limits. We want a tight distribution. So it's a fundamental principle of quality is that you want your quality characteristics to be on target with low variation. That's very important. Now, in Industry 2.0, I picked out what I think are the four most important contributions. Others may disagree. It'd be interesting to have a discussion about that. But hoteling, you may have heard of hoteling from courses in multivariate analysis. They came up with methods that apply to more than one quality characteristic. Suppose we're not just measuring one quality characteristic, but suppose we have 2 or 3 or 4, and they could be correlated. So hoteling came up with a method for monitoring with multiple quality characteristics. Richard Freund, who worked for Kodak, came up with the acceptance control chart. If you have a really capable process, he said, well, maybe we can let the mean move a little bit, put some slack into the process for highly capable processes, which I think was a very good idea. Roberts came up with the exponentially weighted moving average chart. Now, we're collecting data over time. Well, we're collecting data over time. We want to monitor the process. We can use some sort of moving average. With an exponentially weighted moving average, the most recent value gets the highest weight, and the other weights, as you might guess, decrease exponentially. So the current value gets the most weight. We give less weight to the older data with the weights going down. That's going to be an important point. I'm going to come back to that in a moment. Page invented the cumulative sum chart, which I will talk about later in my presentation. It has some mathematical optimality properties, so mathematical statisticians like to study the cumulative sum chart. Again, it's an efficient way of monitoring. Now, this in the bivariate case, for example, the hoteling approach in the bivariate case, instead of horizontal limits, we have a control ellipse. So if a point falls inside this ellipse, we would consider the process to be in control. If the point falls outside the ellipse, we would say that that is indication that some assignable or special cause has happened. It's related to outlier detection, but we would use a Mahalo-Novis distance type measure, and this is just an illustration of the bivariate case. Now, in terms of the weighted averages have been studied. Lice studied weighted control charts based on weighted averages way back in the 70s. Again, the idea is if you're going to use a weighted average, the most recent data needs to be weighted the most. Now, you can use a moving average where you weight the last 4 observations the same. People tend to do that. That's a very common filter. But you do not want past data to be weighted more than current data. It doesn't make any sense. Intuitively, what happened today should be more important than what happened yesterday. Now, it turns out that there are a wide variety of methods that, if you look at the weighting scheme, don't satisfy that. So we have studied some of those. I think that good ideas should be supported, but I think bad ideas should be attacked. So, you know, as long as you do your homework, I think it's important to comment if a procedure has poor performance. So these methods that we critique in this paper with Swin and our other co-authors deal with methods where the weighted average puts more weight on the past than on the present, which in process monitoring is not a reasonable approach. A towering figure in quality in the United States and throughout much of the world was W. Edwards Deming. In the 80s, people in the United States realized that we couldn't compete with Japan. We couldn't compete with Japan based on cost or quality. There was somewhat of a panic, and there was a quality revolution. Due to this competition, we had total quality management, Six Sigma, statistical process control, a big emphasis on design experiments, and Taguchi methods. Inichi Taguchi was a Japanese engineer that came up with some design of experiments methods. Very good ideas, but the implementation wasn't always good. But Deming was the spiritual leader of this quality revolution because he was given much of the credit for the Japanese success because he went to Japan after World War II and taught courses on quality control. So I would encourage you, if you're not familiar with Deming, to Google him at some later time to see what he had to say. Again, he's very, very much of a giant in the area. The Japanese have a prize named after him. The American Society for Quality has a medal named after him. The American Statistical Association has a lecture named after him. Very influential statistician, probably the most well-known statistician ever outside of our community. He had different principles he taught. My students were always interested in the fact that he advocated abolishing grades throughout the entire schooling. He didn't like grades. Well, that topic could be debated whether that's a good idea or not, but he thought it discouraged people. So Deming was given a lot of credit. I think, however, that this individual, Homer Saracen, deserves more credit than most people have never heard of him, but he went to Japan in 4 years before Deming. He was an electrical engineer. He was young, 29 years old, and he was sent there to rebuild their radio communication network. He published books in Japanese on quality management and on statistical quality control, and very forward-thinking books. And he had some ties to Western Electric and Schuhart, but he promoted some of the ideas of total quality management. It's a very interesting story. He's interviewed on YouTube if you want to listen to him be interviewed about his experiences, but he had trouble trusting the translation, English to Japanese, Japanese back to English. So he actually learned the Japanese language so he could communicate with the people directly, which I think is very impressive. His cause has been taken up by Nick Fisher in Australia. That's a picture of his graduating class in 1950 in quality management. These four individuals here to the right, the man on the far right is the founder of Panasonic. So I've read what Deming taught in Japan. I've read what Homer Saracen taught, and to me, there's no comparison. Homer Saracen presented a blueprint for actually implementing quality methods, which I think was very influential there. Now, major advances in the Industry 3.0 period, we had additional multivariate methods. For example, we had a multivariate exponentially weighted moving average chart. Data started being collected more frequently, so we tended to see positive autocorrelation. Data collected close in time can be closer in value, so we had to take into account autocorrelation. Manufacturing processes tend to be multi-stage. So you can't really meaningful monitor the output without taking into account the input. So that became important, monitoring the multi-stage processes, functional image and video data. We did some work on network surveillance, monitoring large, sparse matrices of count data. And I think probably most important here are the public health and healthcare surveillance applications, where there's an emphasis on count data that we see, for example, during the pandemic. And in healthcare, there's much focus on count data and waiting times. For example, in monitoring surgical outcome quality, for each patient, there's a Bernoulli random variable either that patient lives for 30 days following surgery or doesn't. So there's a lot of count data in healthcare applications. And if you've been involved in the healthcare system, waiting times are definitely important as well. Now, in the course of my career, I've probably listened to thousands of presentations. I'm sure some of you have listened maybe to even more than I have. There's only been a handful that I could point to and say, this really is going to change what I'm going to do in the future. A big impact on research direction. But when I heard Bob Brill give this talk at the Fall Technical Conference, he worked at a chemical company, and the quality of his product was determined by a curve, not by a single point, not by 2 or 3 quality variables. It was functional data. This function characterized the quality of his product. So this area became very, very hot. This is a slide from his presentation, actually. This area became very hot. If you can fit a parametric model, linear or nonlinear regression model, then what you could end up doing is just monitoring the estimated parameters. But frequently these curves have odd shapes, and it's better to use some kind of smoothing or non-parametric regression method. But it's a combination of functional data analysis and process monitoring. There was a Wiley book written on the subject, and probably 1,000 papers in the last 20 years written on profile monitoring. Now, as a little aside here, this paper was published 20 years before I heard Bob Brill's talk. It was written by a professor at Virginia Tech, who used to be one of my professors and one of my former PhD student comrades. Now, if you read here, it says control charts are given for monitoring and a model against changes in form, changes in coefficients, and changes in process variance. This is profile monitoring, but it was so far ahead of its time, it didn't really have much of an influence. And it turned out that this paper never really had much of an influence. But that's not all the way it works out. Sometimes papers are written and they are ignored or overlooked for years, and then there becomes interest in what the author had to say. These are called sleeping beauties. So this paper was written on defining and identifying sleeping beauties in science. 2 of these papers were papers in statistics. And one of them, written by Carl Pearson. So if we look at Ronald Fisher as being the father of statistics, then Carl Pearson could be called the grandfather of statistics. On lines and planes of closest fit to systems of points in space. Okay, that sounds like something that's important. Written in 1901. When did it awaken? 100 years later. This paper was asleep for 100 years. Now it's been cited almost 14,000 times on Google Scholar, and this is the pattern. I bring this out just because I think it's an interesting phenomenon. It's not really directly tied to process monitoring, but I thought you would find it interesting that this paper was flatlining here for 100 years, and then there became a lot of interest in it. So I think maybe a lot of us think, well, maybe my papers aren't getting attention now, but maybe I have a sleeping beauty in the bunch, right? Well, maybe we do, maybe you do. But the thing is, it's not going to help you too much in terms of promotion, tenure, or whatever, because it's going to be delayed for, maybe delayed for a century. So an interesting phenomenon. Right now, one of the main points I want to make, I think one place that we've gone wrong in statistical process monitoring is focusing on developing methods that are more and more sensitive to smaller and smaller changes in the process. We don't want a smoke alarm in our kitchen that's going to go off if somebody strikes a match. Warning systems have to be tuned for the application. So Richard Freund, who I mentioned a minute ago with respect to the acceptance control chart, pointed out that sometimes changes are small, but they're so small they're unimportant and we don't want to detect them. So I believe that this is increasingly the case. So there's some adverse consequences of false alarms and these nuisance alarms. A nuisance alarm would be detecting the match being struck in your kitchen. The monitoring could be ignored if there are too many alarms. It's the black tape solution. The warning light goes off all the time. There's no problem. Somebody just puts a piece of black tape over it. Problem solved. Adjusting a process unnecessarily increases variation. If you react to all random variation, you will double the variance. Investigations cost time and money, and we can be distracted from more important problems. So I want to make a tie here. I think it may be obvious already that control charting, the way Schuhart designed it, is very closely tied to hypothesis testing. Therefore, it's going to inherit all the problems that we see in hypothesis testing. The whole practical significance versus statistical significance issue comes into play. And as you know, statistical significance has been attacked quite heavily over recent years. The whole p-value controversy and so forth. I think p-values and statistical significance has its place, but we also have to consider practical significance. Some journals in the United States in social psychology have not only banned p-values, they've banned all of statistical inference. So, I mean, there's really been a backlash against statistics over this statistical significance issue. To understand the issue, I think you have to understand how we assess the performance of process monitoring. We look at the average number of samples or average number of observations until we get a signal. This is similar to an OC curve in hypothesis testing. So if we're comparing two methods, we want the average run length, the average number of samples until the signal to be set the same. Here it's 500. And then the one that drops off quickest is said to be better. But I think you can see the problem here is that we start dropping off more and more quickly. We're going to start detecting things that are unimportant because this shift here is measured in units of the standard error. One standard error could be inconsequential in practice. So we have to take that into account. The whole method that we use to compare methods in statistical process monitoring, in my opinion, needs to be reevaluated to take into account practical significance. But I have to say, it's like trying to steer the Titanic. You know, I mean, we can say this over and over again, but actually getting it something this fundamental changed is not easy. So this just repeats what I said. The average run length is important. We want a high average run length in control, low average run length otherwise. Standard approach, like in hypothesis testing, you would set probability of type 1 error the same and compare power. We're setting the in control ARL to the same and comparing out of control ARL. I think it's important to look at what's called steady state ARLs, where any shift in the process is delayed from the start. We don't want a smoke alarm that is only effective at detecting fire if the fire is already burning when we install it. We want something that's going to be effective if there's a delayed fire, right? So Schwinn has written on this topic. So this whole issue of basing small, medium, and large on units of the standard error, I think is the wrong way to go, because we need to base small, medium, and large on what the practitioner says is small, medium, and large. We don't want a theoretical method where the resulting optimal method would be useless in practice. All right, so our solution to solving this problem is to use the cumulative sum chart. So in this chart, the upper part of the plot here is monitoring for an increase in the mean. The lower part, we're monitoring for a decrease in the mean. We don't let the upper Q sum go below 0. We don't let the lower Q sum go above 0. If we cross one of these red lines, then that tells us that we've had a change in the mean, either an increase, as it's shown here, or a decrease. But if the process is on target, both of these Q sums have pressure toward 0. There's a parameter in there that controls the sensitivity. It's called the reference parameter. All right, so this is my slide with the formulas. I promised you one slide with formulas. We look at the simplest possible case. We have IID, normally distributed means, target value, mu naught, standard error, sigma naught of the square root of n. We standardize the sample means, and we put them in these formulas. We have a formula for the upper Q sum, a formula for the lower Q sum. This parameter K determines the sensitivity. So the reference value K is said to be set to theta 1 over 2, where theta 1 is the smallest shift that we're interested in detecting quickly. It's measured in terms of the standard error. The smallest shift that we're interested in detecting quickly, divided by 2, put that in there for K. And we signal if we have either of these Q sums across the control limit. All right, so this is a relatively simple idea. Now, the problem is most people just set K equal to 0.5. That's the default standard in software. 0.5 says that we're interested in detecting a shift of 1 standard error. Okay, we might not be interested in that at all. So this could be too sensitive and lead to an unnecessary number of nuisance alarms. So we think that reference value should be set to meet the needs of the application. And our fix is to change K. It's a very simple fix. And then we can use H to control the rate of false alarms, the control limit H. Now, under our approach, there's an in-control region for the process mean. In-control region, the limits negative theta naught to theta naught. Instead of a single point being considered in control, we have a region. And then we have a region of out of control values with boundaries at theta 1 and minus theta 1. And we have an indifference region in between there. Now, this approach has been used in hypothesis testing sometimes. Instead of just having a point null hypothesis, you could put an interval in the null hypothesis. And that is very similar to what we're recommending here. But if you take this approach, which some people criticize because they like the standard Q sum, which I always say, well, you just let theta naught be 0. Then you have the regular Q sum. But if you take this approach, then the reference value should be the average of theta naught and theta 1. It makes it a bigger reference value, makes the push towards 0 stronger. This is not a new idea. All of these authors here, including George Box, Doug Hawkins, retired from University of Minnesota, Manuel Yaschin works for IBM, has been using this at IBM for decades. Every single one of these authors recommend theta naught plus theta 1 over 2. So it's not a new idea, but I think it's more important now that we take this approach because we have more data, we have more sensitive control charting than what we really need to have. If you take this approach, M0 here is the in control region, M1 is the out of control region. I'm comparing the regular Shewhart chart, average run lengths to the Q sum, and you can see the numbers I have circled up there are much bigger. They just shows that we have far fewer false alarms and far fewer nuisance alarms. So, but this is a fundamental change in the way that I think methods should be compared in process monitoring. Shewhart charts with wide limits have been recommended for these highly capable processes, all the way back to the 1950s. The acceptance control chart of Freund was involved in just taking the 3 sigma Shewhart limits and just make them wider. But we find that the Q sum chart has much better performance, but this is better than not doing anything, certainly. But they based their 3 regions, the 3 regions for theta, based on the percentage of non-conforming items, which is not really a good idea these days because companies don't want to have 1% non-conforming items. They don't want any non-conforming items. So the method for determining their limits, I don't think really applies, but the idea is still very useful. Now, Deming, there's a picture of Deming here. He was kind of a gruff guy. This is, I guess you could say, his happy face. He was very critical of American management. He was kind of a scary guy, I think. But he referred to modified control limits on the Shewhart chart as being bear traps. He didn't like anything but the regular 3 sigma limits. In the index to this book he wrote for modified limits, he put never in there. So if you never looked at what he wrote and all you did was look in the index, you would understand what he thought, right? Never use modified limits. So he wrote, with continual improvement, distributions should be so narrow that the specification limits are lost beyond the horizon. Well, this is a very idealistic view, but in practice, we can't always have this as being our goal. For example, the chart on the left here is a control chart in a pharmaceutical application where we have quite a few points outside the 3 sigma limits. So the standard approach would be to investigate these. But if you plot these data against the specification limits over here on the right-hand side, you can see that we have very little variation going on here. Chances are, we would say, we have bigger fish to fry than to try to improve this process. So this is the kind of application where we definitely need to put some slack in the process and not signal these alarms. Now, this approach of trying to detect relevant changes has been applied in other areas. For example, these 2 authors applied it to time series, detecting relevant changes, not any change, but relevant changes. I think this could be applied in other areas as well. All right, so to finish up my presentation, I want to talk a little bit about Industry 4.0. It encompasses many different areas: cloud computing, big data, automation, additive manufacturing. Each one of these is a very challenging area within itself. Includes a lot of territory. The data are in Industry 4.0. We have a lot of sensor technology. We put sensors on everything. We have multi-stage processes. We have high dimensional data, a lot of input data streams. We need dimension reduction in many cases. We have high and varied sampling frequencies. Typically, process variables are measured much more frequently than quality variables. We have images, we have video, we have attribute data. We have data in many forms. So you can see it meets all the characteristics of big data. We have complicated relationships among the variables. Could be correlation, could be causation. So it's a very challenging situation here, and current methods are not really able to handle it very well. I think artificial intelligence comes into play here, some machine learning methods. I think the concepts of process monitoring are going to apply, but the methods are going to have to change. Now, studies have shown that a lot of companies in the United States don't know what to do with all this data. They're a lot better at collecting data than analyzing and using the data. Collecting data requires one skill set. Analyzing it requires another skill set. So a lot of companies don't have the in-house expertise to use all of this big data. So software companies are coming into play to come in to companies and help them out. One of them is Process Miner here that you could look up on the internet. I mentioned it solely because they made me a scientific advisor and I felt some kind of obligation to throw it in. But this is only one of many companies out there, software companies that will come in and help companies make sense of the big data. So a lot of companies are spending a lot of money putting in sensor technology, but then once they get the data, they're not really sure how to really take advantage of it. Now, in Shewhart's day, if you had a manufactured part, maybe you could measure 1 or 2 dimensions on a sample of those, but there are laser scanners now where you can create a virtual replica of your part using laser scanners. It's amazing how much more data. Now we have a cloud of data points instead of just 2 or 3 data points on each part. Now I have a motivating example here I want to conclude with this. This is from a slide given to me by Jan Shih at Georgia Tech. just illustrating some of the issues involved in current manufacturing. This is a multi-stage process, semiconductor manufacturing, but this is a very highly summarized set of stages here because there are hundreds of stages. We have heat maps, we have images, we have attribute data. At each stage, we have a different kind of data, and we want to try to figure out what's going on. What characteristics in the early stages affect the final outcome at the end? It's a very, very challenging area and plenty of opportunity for statisticians to get involved. First of all, I think Homer Saracen deserves much more recognition than he's gotten. It could be too late because the quality revolution is past, but I think he deserves as much credit as Deming and Joe Duran for his contributions to Japanese quality, which, by the way, was transferred to the US and throughout the world, their quality principles. Now, statistical process monitoring methods have evolved over the years because the increase in data wasn't a step function, it was a gradual increase in the amount of data. So SPM methods have been adapted over the years. We need steady state. If we're going to compare methods, we need steady state comparisons where any shift in the process is delayed. There's some methods that look really good if the shift is assumed to occur at the very beginning of monitoring, but not so good otherwise. Now, one of my main points here, we need to tune process monitoring methods, which in many cases means desensitizing them, which goes against the current thought in research on process monitoring. And finally, Industry 4.0 offers many challenges, and I think machine learning and AI will come into play here. So thank you very much for your attention.